welcome to your prep video for 4.1. In this video, we will be working on things like maximums and minimum values. We start with absolute extreme values. Extreme is just, your extremes, your highest and your lowest. Same thing as absolute max and absolute min. Now, in other books and maybe in WAMAP, sometimes absolute max min is called a global max or min. Okay, and so when we have an absolute max or min, that means our function value for an absolute max at a certain point is larger than any other point on the graph. So this would be our absolute max. So this says f of c is greater than or equal to f of x for every x in the domain. Values that are not in the domain are not even considered. Now for our absolute min, f of c is less than or equal to. So here is an example where we have an absolute min right here. Now I've just shown parabolas for a reason, that this has no absolute minimum value, because these values go down forever as x gets really, really large or x gets really, really small. The f of x values continue to decrease. So there will be no absolute min on this. Not every graph has an absolute min or an absolute max, and some can have neither. So if you had a graph that looked like this, and you have these open circles right here, this would have neither an absolute max nor an absolute min, because we can keep getting closer and closer to this endpoint value b and never reach this output value f of b. Or this, okay, so that's not fair, because f of b isn't defined. So I would say that, let's say that this is 5. So all the values as you get closer and closer and closer to b are getting closer and closer to 5, but will never reach 5 because that value is not included. So there's no absolute max. Now over here, there'd be no absolute min because, say this is 2, as you get closer and closer to your starting value a, you will get closer and closer to output values of 2, but you will never reach 2. There are limits. The limits exist, but the function values don't. So there is no absolute max and no absolute min. Okay, so we have an absolute max or an absolute min. Here's another function that has no absolute max or an absolute min, an odd power function. So no max, no min, no absolute max, and no absolute min. So the reason why I'm making sure to to identify them as absolute maxes or absolute mins is because there are two types of extreme values. You have your global or your absolute, global/absolute. That's one type of absolute value. The other ones are local or relative. That's the other, relative max or min values. So the book that we're using uses absolute maxes or mins, and they use local max mins. You will see in WAMAP that sometimes it's called local and sometimes it's called relative. I kind of spelled relative wrong. There we go. So we want to make sure that we are identifying what type of absolute max or absolute min or global max, global min, local max, local min that we have found. We don't want to just say, we don't just say min or max. I mean, you could say that, but you would not be clear. And you don't always have a graph that you're working with. So these max and min values, also known as extreme values, has this theorem that if you have a closed interval, you are guaranteed an absolute max or an absolute min if that function is continuous. So continuous on the closed interval. For example, if you have f of x squared, f of x equals x squared, this is continuous. But let's shorten its domain, -2 to 2. We know that this graph looks like this. It goes from -2, it's equal to 4, and at 2, it's equal to 4. So it looks like this. Here, we have an absolute max and an absolute min for this function. So this is a special function, right? It's not the f of x squared function alone, it's the f of x squared function on the interval from -2 to 2. We have a closed interval, and we have a continuous function. So that means we are guaranteed an absolute max and an absolute min. Now, if you notice, our absolute max value right here is at the output value 4. So the absolute max is at x equals -2 and x equals +2. The a max value is 4. So the x values tell us where it's located, and the y value is the maximum output value. Here we also have an absolute min. So we can say f of x has an absolute min of 0 at x equals 0. So if you have a closed interval and the function is continuous, so closed interval and continuous, you are guaranteed both an absolute maximum value and an absolute minimum value. And there can be ties. So we can have two x values that have the same absolute max and absolute min. I mean, the most boring function would be a constant function where you have an infinite number of absolute maxes and absolute mins. So both the absolute max and the absolute min are the same thing. So a max equals a min at all points on A to B. So that, I mean, that's boring. We wouldn't really spend too much time investigating that type. We wouldn't have to use any calculus for that. Parabolas, again, we don't have to use calculus, but we practice using calculus for these sorts of things. But once we know that we have a closed interval and a closed interval on a continuous function, then we now have ways of figuring out where and how to find these extreme values. And so this is where we first define, before we start doing that process, we'll first define local extreme values. So with a local extreme value, it's more like you have this big function. Let's draw it. Okay. And if you zoom in on a small interval, let's say this interval to this interval. So if we only look at the function from here 0 to, let's say this is 5, we would be looking at this part of the graph. Now on this interval, this point right here is a maximum value. Every value on either side of it decreases away from it. So this would be called a local max. And so would this one, because every value near it decreases as you move away from it. And this would be a local min. And this right here is also a local min. Right? So here it says that f of c is greater than f of x on an interval, and f of c is a local maximum value if f of c is greater than f of x on that interval. So right here, it is greater than all of its values. Here and here. Okay? And so, again, so f of c, the output values are less than all other output values on that interval. So it's a local minimum. So let's see, for shorthand, I'll let you guys use L min, L max, and A min. My joke. Can I get an A min? And A max. It's not any fun telling you guys my jokes when you're not here to groan at them. You can hear my kids in the background? No, they're not paying any attention to me. All right, so these are the shorthand that I use. And I encourage you to use them unless you want to write out local maximum. Let's try that again. Maximum. You could write all that out, or you can just use L max. Okay, and so what we found is if I zoom in on this portion of our graph, this L max right here happens to have a tangent line that is 0. And if we look at this one right here, or here, let's say this one right here, it has this cusp, or this corner. So right here, f prime of c is equal to 0, and right here, f prime of c is equal to u and d. So it's undefined, because if you look at the slope from the left, and you look at the slope from the right, so the slope from the left is negative, and the slope on the right is positive, and it changes suddenly. There's no smooth changing curve. And because it changes suddenly, it is undefined at that point, because the limit from the left is not equal to the limit from the right. But on these ones, it slowly approaches 0 as positive slopes, and then it goes negative slopes as it moves away. So this would be smooth. This is a corner or cusp, so not smooth, meaning the derivative doesn't exist. So if we can locate these critical points, we also now can put these things together with, I'll come back to this example in just one second. We can put all these things together to describe our closed interval test. So this, if you can locate a closed interval, this is the fastest way to figuring out whether you have a absolute value or an absolute max value or an absolute min value on your interval. And a lot of our modeling functions in the real world, well, okay, so our word problems that we'll have to find maximum min and minimum values, when we call those optimization problems, we'll be using this closed interval test anytime we can bound our domain. So when we model functions of real life things, the whole real line doesn't always work, especially if we're working with time. So our model isn't described when time is equal to negative, because that's before, say, we set off a rocket or anything. So if we can close and bound an interval, it'll be much faster to find our absolute maxes and absolute mins. And so what we found out is that if we take a closed interval, let's see, here's my function. If I close that interval, I lost it. Let me switch back to what I was doing. If we take here to, let's say here, okay, we are going to look at the endpoint values and at the local minimums and local maximum values. So the closed interval test says that if we have a closed interval of a continuous function, then our possible absolute maximums and minimum values will be located at an endpoint, which I call EP. So these two are our endpoints, and interior critical points. Critical point. Critical point. Critical point. Oops. Critical point. If we had, say, closed our interval here, so if we had gone from here to here, then we would have tossed out this critical point because it would not be on our new interval. So it has to be interior critical points. So only this critical point and this critical point would be tested. So over here, if you look at my little table, you'll make a table of values. And I suggest that you put them in order. So you'll start with your endpoint A, go to your first critical point, your second critical point, or however many critical points you have, and then put in your end point. Any critical point that does not fall between A and B needs to be thrown out. If you add those to your table, students tend to accidentally pick those ones. Don't pick that one. So once you find your endpoints and your critical points, you then make a table of values. You find your function values for your endpoints and all your critical points. And then you just look. This one is a max. This one is a min. And everything else is neither. So I usually write, so this one is the A max value, and this is the A min. And then you can write neither, or you can leave it alone. All right, so let's go back up to my example right here. I'm going to use my eraser. Clean this up a bit so that we have some points in this function. So we first need to find what the derivative is, and then set it equal to 0 and look for any values that it doesn't exist. But before we do that, if we look at this function, the domain of this function is x greater than 0. And that's because the ln of 0 does not exist. But every value up to 0 does. So remember, the ln of x function looks like this. Right? So it has a vertical asymptote as you get closer and closer to 0. Now, if I take the derivative, f prime of x, I have a product rule to use. So I left rewrite it, plus right left. Oops, I start taking the derivative. And that's going to equal x squared times 1 over x plus the ln of x times 2x. Now this is one of those occasions that we are doing something else with our function. So I'm not going to leave it like this. I'm going to make it pretty so it's something that I can work with. So here, one of these x's will cancel. So that turns to 1 and that turns to 1. And I'm left with an x here plus 2x times the ln of x. Okay, and I can factor out an x, so I get x times 1 plus 2 ln of x. So f prime of x equals 0 So I can say equals 0 when x equals 0, or 1 plus 2 times the ln of x equals 0. But we cross this one out because x equal to 0 is not on the domain of f of x. So that won't be a critical point. But, let's see, I'll cross that out with red. But 1 plus 2 ln of x is equal to 0 when 2 ln of x is equal to a negative 1, or the ln go away, or the ln of x is equal to a negative 1/2. Now to solve for x, I exponentiate both sides. So I get, so e to the ln of anything is that anything, and this is e to the negative 1/2. So I have a critical point when x is equal to e to the negative 1/2. And I can find that value since f of x is equal to e, whoops, not e, x squared ln of x, we get f of e to the negative 1/2 is equal to e to the negative 1/2 squared times the ln of e to the negative 1/2. Now this is just equal to e to the negative 1, and the ln of e to anything is that anything, so this is times a negative 1/2, which is equal to a negative 1 over 2e. So we have a critical point at e to the negative 1/2, comma, or I could put that 1 over the square root of e, comma, negative 1 over 2e. So that's where our critical point is. We could say that the function is the derivative is undefined at 0, but since the derivative function is undefined at 0, but since that is not on the domain of f, then it is not a critical value. And let me show you the graph of this. So if I come over here, I have my graphs. Here's our graph of f of x squared equals, point is somewhere right here. And so that would be our e to the negative 1/2, comma, 1 over 2e. And so this is a critical point. And we can see from our picture that it is a local minimum and actually an absolute minimum. So right here, we can say that f of x has a local min and a local, an absolute min at x equals e to the negative 1/2 of 1 over 2e. So the value is 1 over 2e, and it's at x equals e to the negative 1/2. Okay, so we come back here. Those are critical values, or a critical point. Now we're going to practice finding absolute max or mins on a closed interval. So here's our example. Find the absolute max and absolute min for f of x equal to x to the 4th minus 2x cubed on the interval negative 2 to 1. So this is continuous. F of x is continuous. Because we know it's continuous because it's a polynomial, which is everywhere continuous. And so, and this is a closed interval, so -2 and 1 are included. So the next thing we're going to do is we're going to take the derivative to find our critical values. So find all critical points or values. So f prime of x is equal to, so the derivative of x to the fourth is 4x cubed minus 3 times 2 is 6x squared. So we're going to look for f prime of x equals 0 or f prime of x u n d. But the derivative is a poly. F prime of x is a poly, so it's everywhere defined. So I don't have to check right now for it being undefined. I only have to check now where it's equal to 0. So I'm going to factor out an x squared and a 2. So 2x squared leaves me with 2x minus 3. And I can see that this will give me, this is equal to 0. So 2x squared times 2x minus 3 equals 0 when x is equal to 0 or 2x minus 3 equals 0. Because we have product, if one of the product pair is a 0, then the entire thing is a 0. So this is 2x equals a positive 3 because I added 3 to both sides. Now if I divide by 2, I get x is equal to 3 halves. And x is equal to 0. So the entire function of f of x to the fourth has these two critical points. So right now I'm going to start and make my table. I have x. My endpoint here is -2, so this is an endpoint. Then I have 0, which is a critical point. And then I have 1, which is an endpoint. And then I have 3 halves. Now this we throw out, because it's not on the domain. Well, let's say it's not on the interval -2 to 1. Had we found a critical point at -3, we would have thrown that one out as well. I just didn't use an example of that here, and I didn't draw that on in my box up here. Okay, so we're not even going to evaluate f of x at 3 halves. So now we find the f of x values. Okay, now later in my next lesson, you will learn about how we fourth minus 2 times -2 cubed. This ends up being 32. Then if I plug in 0, I get 0 to the fourth. Minus 2 times 0 is equal to 0. If I plug in 1, I get 1 to the fourth minus 2 times 1 cubed, which is equal to -1. So this value right here, 32, is the largest value. So we have an A max. This value right here at -1 is a minimum. It's smaller than all the other values, so this is our absolute min. This is neither. And so then what we can say now is that f of x has a max value of 32 at x equals -2 and an absolute max value of 32 at x equals -2 and an absolute min value of 0 at x equals 1. And that is our absolute max and absolute minimum test. All right, so if you were going to go ahead and do some board works after this, I will post those, but you should read the section, and then you will have class activities tomorrow on this material. Okay, talk to you soon.